Greetings and salutations, magical chemists. Let's talk about the temperature dependence of Kw, the equilibrium constant for the dissociation of water. So we are going to consider the simplest possible dissociation of water, which is H2O breaking apart to form H plus and OH minus. If that happens, do you think that's an endothermic or exothermic process, and why? Take a moment and take your best guess, and then we will check. Did you realize it was endothermic? Because if you are breaking or ending a bond, it's always going to be endothermic. It takes energy to overcome the attraction. That means that we can rewrite the dissociation of water as a thermochemical equation. In case you've forgotten what that just means adding in heat to the reaction. Well, if it's endothermic, that means heat is a reactant. Now that we have a thermochemical equation and we know where heat is located, we can actually predict what will happen to Kw if we heat or cool the solution. Well, in this case, pure water. So we are going to cool a solution of pure water, and we want to predict the direction the reaction is going to shift. You can do this using the glories of Le Chatelier, so you should try it. And when you're ready to check your answer, unpause the video. Cooling a solution of pure water, of course, lowers the temperature, which lowers the amount of heat, thus lowering a reactant. And Le Chatelier says, if you stress the system by changing one of the reactants, in this case taking it away, it's going to shift to replace it. So that means it must shift left to produce more heat and reestablish equilibrium. Knowing that the reaction will shift left allows us to predict the effect on Kw, because of course changing the temperature is the only change that will actually change the numerical value of K, including Kw, because it's just another equilibrium constant. So I would like you to predict, do you think Kw will increase, decrease, or stay the same, and why? And when you're ready to check your answer, unpause the video. Well, if you shift left, you are increasing your reactants, but you're decreasing your products. And since K is products over reactants, this will make Kw go down. So then the question becomes, okay, that's great, but would you expect the concentration of the protons to increase, decrease, or stay the same? You guessed it, you're going to predict, and then when you're ready to check your answer, unpause the video. Remember how shifting left decreased the concentration of products? Well, H plus is a product, so of course its concentration will go down. Okay, well the concentration of H plus decreased, so we want to figure out what that does to pH. Hopefully you remember that this would actually cause the pH to increase, because an increased pH is less acidic. Now we want to know what happened to the hydroxide ion concentration. Well, hopefully you realize that hydroxide is a product just like H+, so the concentration of hydroxide will also go down. And of course, if the concentration of hydroxide went down, the pOH goes up. Okay, so now we figured out what happened when we cooled the water, what happened to our concentration of our protons and hydroxide, and the pH and pOH. Well, remember this equation that we know and love, pH plus pOH equals 14? The question is that still true? Go ahead and see what you think, and when you're ready to check the answer, unpause the video. Would you be shocked to learn that no, this equation does not hold true? Remember, both pH and pOH increased when we cooled the water. So when you add them together, you're going to get a number bigger than 14 when water gets colder. Okay, knowing what we know, now I want you to predict what's going to happen if you heat a solution of pure water. What's going to happen to pH? And would that make your solution of water more acidic, more basic, or still neutral? Let's try it, and when you are ready to check your answer, unpause the video. Well, if you heat up the water, in this time the pH is going to decrease. Remember, heat is a reactant, so we're adding heat. Le Chatelier says we need to shift right to use up the heat. Well, that produces more protons. More protons, lower pH. You might be thinking that because the pH decreased, your solution of water is now going to be more acidic, but actually it's still neutral. Even though the concentration of protons went up, so did the concentration of hydroxide. And remember, neutrality is determined by the concentration of H plus being equal to the concentration of hydroxide. So it doesn't matter that the pH went down. Crazy story, your water is still neutral. Okay, so now hopefully you understand the temperature dependence of Kw. The good news is, as far as the math is concerned for actual pH and pOH calculations, we are always going to assume that we are at 25 degrees. So you do have to be able to look at pure water and figure out what happens to the pH and pOH and its Kw if you change the temperature. But other than that, anything other than pure water, you don't have to worry about it. Now, please make a note, because this is probably the most important thing on this whole page. This is what we talked about at the very beginning, that the dissociation of water is endothermic. You can always reason it out using what we talked about with the bond breaking or ending, but there are a lot of problems that require you to work out the fact that the dissociation of water is endothermic, so knowing that fact will be very helpful. And that's all we have about Kw and its temperature dependence. Thank you for playing with the glories of chemistry.